Galileo Galilei entered the world on February 15th, 1564, in the riverside city of Pisa, then a Roman-flavored settlement of red rooftops, cathedral bells, and bustling mercantile life. His birth coincided with a Europe trembling between old belief and new discovery, a landscape where astronomy still leaned on Ptolemy, even as daring minds whispered of revolutions in the stars. Pisa's leaning tower, its marble baptistery, and its noble squares formed the scenery of his earliest days. Yet it was not architecture alone that shaped him. It was the atmosphere of inquiry carried quietly within his home. Galileo was the first of several children in a household where music, mathematics, and financial hardship lived side by side, teaching him early that genius grows not from comfort, but from hunger. Hunger to understand, to question, to prove. His father, Vincenzo Galilei, was a skilled musician, theorist, and restless intellectual, a man who challenged old musical scales with new mathematical reasoning. Around him, music was not merely sound, but measured vibration, rhythm governed by ratio, harmony shaped by number. Young Galileo watched his father pluck strings and debate tuning methods with scholars and artists, and from this he absorbed something vital, that no rule was sacred if nature disproved it. His mother, Giulia Aminati, provided the other half of his formation: discipline, resilience, and devotion to family in times when money was scarce and opportunity unpredictable. Their home was warm, but also demanding, built on effort rather than ease. In this environment, Galileo learned early that thought must be sharpened by labor, not privilege. The Galilei household valued culture, yet lived close to financial edge. Vincenzo's wages fluctuated, and the family frequently shifted between comfort and careful budgeting. This instability taught Galileo to observe the world not as fixed truth, but as something that could tilt and change, just like a musical scale or the course of a planet. Even as a child, he was known for taking objects apart, for watching light fall through windows, for asking questions that many adults answered with sighs rather than explanations. Curiosity became his native language. Pisa's streets, filled with scholars in their black robes, university bells, and merchant chatter, provided scenery. Home provided fuel. Together they formed the cradle of a scientist destined to challenge the universe itself. Meanwhile, the intellectual climate of Renaissance Italy seeped into Galileo's childhood like ink through paper. The works of Archimedes, Euclid, and Arabic mathematicians circulated among scholars and musicians who passed through his father's circle. His early life was not one of laboratories or telescopes, those would come later, but one of ideas, sound, proportion, and daring thought. Galileo grew amid argument and melody, numbers and necessity, absorbing from his father the conviction that authority must bow to evidence. His birthplace did not crown him, it prepared him. Pisa gave him stone towers and river tides, but his family gave him the habit of questioning, and from that habit would rise a mind that would turn telescopes towards the heavens and shake the foundations of the world. Galileo's childhood education began not in academies of grandeur, but in modest rooms lit by Tuscan sunlight, where ink, parchment, and the voice of instruction shaped his earliest thoughts. He was first taught at home, where his father introduced him to the grammar of music, the pulse of rhythm, and the logic hidden in sound. Unlike most children of his age, Galileo did not learn in silence. He learned in vibration, in measured tones on a lute string, in the comparison of one interval to another. Numbers came to him not as symbols on a page, but as living relationships reflected in resonance and pitch. This connection between mathematics and the physical world would later define his science, but its roots were sown in these early lessons at his father's side. When he reached school age, Galileo was placed under the instruction of Catholic tutors who trained him in Latin, the key language of scholarship, and in classical literature. The young boy proved adept with language, memorizing verses and composing small speeches with clarity beyond his years. Yet it was not merely the words that captured him. It was the mechanics behind thought. Teachers noticed that he often paused mid-recitation to ask why a phrase had been structured a certain way, why logic required such a form, why rhetoric convinced without force. Even as a student, Galileo treated argument like music, something to be analyzed, balanced, perfected. His talent did not lie only in memory, but in interpretation. And in this, his future path began to gleam faintly, like a distant star just before dawn. Outside the classroom, Galileo's curiosity expanded into the physical world. He spent long hours observing everyday motion. Water swirling in basins, insects climbing walls, church chandeliers swaying like pendulums in cathedral air. While other children played without thought, Galileo measured play with mind. Why did objects fall the way they did? Why did the swing of a lamp seem constant, no matter how wide its arc? He was not yet a mathematician, not yet an astronomer, but the seeds were unmistakable. He did not accept the world's behavior as obvious. He treated it as a puzzle waiting to be unlocked. To him, nature whispered patterns, and he listened. By adolescence, Galileo showed aptitude in drawing, mathematics, and instrument making, skills that would later converge into invention. He sketched machines, traced geometric forms, and tested simple devices crafted from wood, string, and stone. He had the rare talent of transferring observation into mechanism, idea into form. While education gave him language and classical grounding, his mind insisted on more: evidence, testing, demonstration. The child who watched moving light and heard music as number would one day measure gravity, reinvent astronomy, and defy empires with the truth he could prove. His early talents were not extraordinary flashes. They were steady flames, nurtured in Pisa, sharpened by curiosity, and destined to blaze across the history of science. Galileo's admission to the University of Pisa in 1581 marked the moment his intellect stepped from household curiosity into formal scholarship. He entered the university at 17, not as a scientist. Science as we know it did not yet exist, but as a young man expected to study medicine. His father, mindful of financial security, hoped his son would become a physician, a profession that promised stability in an era where music and mathematics rarely did. The university's stone halls, cloisters, and lecture chambers formed a sharp transition from his earlier learning. Gone were the domestic rhythms of lute strings and home tutoring. Here he encountered anatomy, Aristotelian philosophy, and formal logic taught in Latin by cloaked professors who spoke with authority rather than experimentation. Galileo initially accepted the path before him, attending lectures on physiology, medical theory, and the teachings of Galen. Yet he soon found himself drawn more strongly to mathematics than to medicine. While medical professors spoke of humors and balances within the body, mathematicians demonstrated the certainty of proportion, the elegance of geometry, the reliability of proof. For Galileo, mathematics revealed a world where truth could be measured, tested, confirmed, not merely recited from ancient books. He attended extra classes without prompting, borrowing mathematical texts and spending late nights tracing diagrams by lamplight. Medicine was duty. Mathematics became passion. The university exposed him to the intellectual tension of the Renaissance. Aristotle's doctrines were still revered, but murmurs of challenge were growing. Galileo observed demonstrations that confirmed traditional ideas, yet also noticed contradictions in nature that theory failed to explain. Between lectures, he joined discussions with students who shared his hunger for deeper questioning. In courtyard corridors and under vaulted ceilings, he practiced argument, sharpened reasoning, and learned how to defend a claim not by reputation, but by logic. Pisa's academic environment tested him like a forge, pressing him to confront establishment thought even while obeying its structure. By the time Galileo completed his years at Pisa, he was no longer simply a student, but a thinker in motion, ready to step beyond accepted belief. He left the university without a medical degree, but with something more enduring: a disciplined intellect capable of questioning and proving. Pisa had not transformed him into a scientist. It had given him the tools to become one. The city's classrooms, cloisters, and debates became the foundations of a mind that would later measure falling bodies, challenge cosmic models, and stand defiant before the greatest powers of his age. His enrollment in Pisa was not the end of childhood. It was the ignition of a revolution still unfolding in the story of human knowledge. While Galileo entered the University of Pisa under the expectation that he would become a physician, the seeds of change began to grow almost immediately. The lectures of medical faculty, rooted in Galenic tradition, offered him theory without demonstration, disease explained through balance of humors rather than observable mechanisms. Galileo listened, took notes, learned terminology, yet his mind refused to rest within the boundaries of accepted doctrine. In quiet moments, he found himself sketching geometric shapes rather than anatomical diagrams, calculating ratios instead of memorizing prescriptions. Medicine taught him about the body, but mathematics opened pathways into the principles governing the world itself. The true turning point arrived when he attended informal mathematics lessons, led by Ostilio Ricci, a visiting tutor of geometry. Ricci introduced Euclid not as scripture, but as reasoning made visible, lines, angles, and proofs arranged with undeniable certainty. Galileo watched as theorems unfolded like music, each step justified by proportion and logic. The clarity struck him like revelation. Where medical theory leaned on authority, mathematics leaned on proof. Galileo soon began to follow Ricci beyond official curricula, requesting books, attempting constructions with compass and ruler, teaching himself concepts far beyond what his university expected him to study. It was not defiance. It was discovery. As his focus shifted, Galileo developed a fascination with natural motion, equilibrium, and mechanical behavior. He observed pendulums swinging in cathedral naves, water flowing with constant rhythm, bodies falling with a certainty Aristotle had not fully explained. Mathematics became his instrument for decoding such motion. Philosophy became the lens through which he interpreted physical law. This union marked the birth of his scientific identity. He began to write small treatises, conduct minute experiments, and question the foundations of natural philosophy that scholars accepted without hesitation. Galileo was no longer merely learning. He was investigating. Eventually, his passion overpowered obligation. Galileo abandoned the medical track, despite the financial risk, and committed himself to mathematics and natural philosophy, a choice that astonished some and disappointed others. Yet it was the decision that defined his future. From this pivot emerged the thinker who would measure acceleration, challenge the skies with telescopes, and confront the church with evidence written in the stars. By walking away from medicine, Galileo freed himself to explore the laws of nature as they truly were, not as tradition declared them to be. In that shift, the world gained a mind that would show humanity how to see the universe anew. Galileo's earliest scientific work emerged from simple observations: light swinging from cathedral ceilings, objects rolling across stone floors, water pouring with steady rhythm from fountains. These were not grand experiments, but everyday experiences that most people passed without question. Galileo paused, measured, compared, and returned to the same motion again and again until pattern revealed itself. His first inquiries focused on pendulums, and he discovered, legend says, by watching a chandelier in Pisa's cathedral, that their oscillations appeared regular, regardless of arc length. This realization, subtle yet revolutionary, hinted that nature obeyed mathematical law even in something as gentle as a swinging lamp. Though he lacked instruments of precision, he timed oscillations by his own pulse, marking the moment when empirical rhythm entered scientific thought. From pendulums, Galileo expanded his curiosity to falling bodies. Aristotelian doctrine taught that heavier objects fell faster than lighter ones, but Galileo grew suspicious. He devised inclined planes and measured the descent of balls rolling along wooden tracks, slowing the motion enough to observe what freefall concealed. His trial suggested that acceleration was constant. Mass did not dictate speed as tradition claimed. For the first time, experiment challenged authority. Measurement overturned assumption. Galileo did not yet have the language of gravity, but he had discovered its behavior through method. In modest rooms and narrow courtyards, the groundwork for classical mechanics began to form beneath his hands. He also turned his attention to buoyancy and hydrostatics, developing a fascination with why objects float or sink. Inspired by Archimedes, he studied density, equilibrium, and displacement through small-scale experimentation with containers, stones, and liquids. His early treatise, La Bilancetta, The Little Balance, emerged from this work, demonstrating how to determine density using a hydrostatic balance of his own design. This was more than technical innovation. It was the embodiment of a new methodology. Knowledge drawn not from philosophical declaration, but from demonstration. Galileo's science was born from touch, trial, repetition, and the mathematical description of physical behavior. These early discoveries may seem modest compared to the cosmological revolutions he would later ignite, yet they formed the scaffolding of his future greatness. In analyzing pendulums, motion, and buoyancy, Galileo crafted a new vision of inquiry, one where nature spoke through measurable patterns, and the truth was found not by authority, but by proof. He established the habit that would define his life: to observe, to test, to doubt, and to demonstrate. The young scholar who timed swinging lamps with his heartbeat and rolled spheres down wooden slopes was already reshaping the foundations of physics. His early studies were seedlings of a scientific transformation that, in time, would move the earth in the minds of humanity. Galileo's formal academic life began in 1589 when he secured a teaching position at the University of Pisa. Ironically, the same university where he had once challenged traditional doctrine as a student. His appointment as professor of mathematics was modestly paid and socially precarious, yet it placed him in a classroom where ideas could be tested openly. Galileo stood before students in the shadow of Pisa's famous tower, teaching geometry and astronomy according to the accepted Aristotelian curriculum, even as he quietly dismantled its assumptions through experiment. The famous story, whether literal or symbolic, of Galileo dropping weights from the Leaning Tower reflects this phase of defiance when he demonstrated that bodies fall at the same rate regardless of mass. His lectures were provocative not for showmanship but for logic, stirring both admiration and suspicion among colleagues loyal to classical doctrine. Pisa was a proving ground more than a home. The academic environment was conservative, closely tied to the intellectual authority of Aristotle and to church oversight. Galileo, with his insistence on verifying knowledge through observation, quickly gained a reputation as a critic of dogma. He published early work on mechanics, offered demonstrations that contradicted scholastic teaching, and engaged students in reasoning rather than recitation. Yet his growing boldness and his disputes with university officials eventually cost him favor. By 1592, financial pressures and political tension pushed him to seek a new appointment, one that would allow scientific exploration rather than restrict it. Pisa had sharpened him, but Padua would unleash him. The University of Padua welcomed Galileo into a climate of openness unique in Europe. Under Venetian independence, scholars enjoyed greater intellectual freedom, and Padua was renowned as a center of medicine, astronomy, mathematics, and anatomical study. Here Galileo lectured on geometry, mechanics, and the structure of the cosmos to overflowing halls of students who recognized in him a teacher unlike any other. His classrooms were lively, filled with demonstrations, diagrams, and instruments he built with his own hands. The city beyond the university pulsed with innovation. Workshops, naval yards, and printing houses gave Galileo access to metalworkers, craftsmen, and lens makers who could turn his theories into machines. Pisa had been an academic stage. Padua became a workshop of invention. Over 18 years in Padua, Galileo's career ascended rapidly. He developed systematic studies of falling bodies, refined his understanding of motion, articulated early principles of inertia, and prepared the intellectual tools that would later support his astronomical revolution. Nights were spent composing lectures and constructing mechanical devices. Days were filled with teaching, debate, and incremental discovery. Students traveled from across Europe to learn from him, drawn not only to his knowledge, but to the method that produced it. Padua gave him freedom, audience, and purpose, conditions that transformed him from skilled mathematician into pioneering scientist. When he finally left the city in 1610, he carried with him the results of nearly 2 decades of discovery, stepping into history with the confidence of a man whose ideas were ready to change the world. During his years in Padua, Galileo's mind shifted increasingly toward the creation of devices that could measure, magnify, and reveal the hidden behavior of the physical world. He did not treat tools as accessories to science. He treated them as engines of discovery, capable of extending human perception where the senses alone could not reach. Early in this inventive period, he constructed military compasses, geometric compendiums, and mechanical instruments that allowed engineers and artillery officers to calculate angle, trajectory, and fortification design with precision. These devices were not theoretical constructs. They were practical instruments sold to nobles, soldiers, and scholars alike, helping Galileo support his family while feeding his intellectual restlessness. Craftsmanship became a branch of his science. Wood, brass, and glass joined mathematics as elements of truth. The turning point came in 1609 when news reached Galileo of an optical device being sold in the Netherlands, a tube of lenses capable of making distant objects appear nearer. The original model was crude, magnifying only threefold, but Galileo immediately saw not a novelty, but a possibility. Without ever seeing the Dutch instrument, he began grinding lenses, adjusting curvature, and testing refractive combinations late into the night. After relentless experimentation, he produced a telescope magnifying 9 times, then 20, and soon surpassing every spyglass known in Europe. Galileo was not the inventor of the telescope, but he made it a scientific instrument for the first time, transforming a curiosity into a precision machine. Where others built toys, he built a window. With this improved telescope in hand, Galileo climbed bell towers and hilltops, pointing the instrument toward ships approaching Venetian waters. What had once been mere specks became sails and rigging long before they reached shore. News of the device spread rapidly, and Venetian officials recognized its military potential. Early sight meant early advantage. Galileo demonstrated his telescope before Senate leaders, and the instrument astonished observers who had never imagined distance could be conquered by glass and geometry. Yet the true revolution did not lie in earthly application. It lay in the skies above. Soon, Galileo turned his telescope upward, and the universe began to change. Through his improved lenses, the heavens fractured into detail no human had ever seen. The moon was revealed to be mountainous and scarred, not a perfect sphere. Jupiter shimmered with 4 orbiting moons. The Milky Way resolved into countless stars. Galileo sketched what he saw with restless urgency, each observation another blow to the long-standing belief in celestial perfection. His telescope did not merely magnify, it disrupted the architecture of cosmology. By improving the instrument, he had expanded human sight beyond its natural limit, and with it, expanded thought itself. The invention of these instruments marked the moment when observation triumphed over speculation, when the eye, armed with glass and reason, became the new authority in the study of nature. Galileo did not just change how we look, he changed what we are capable of seeing. When Galileo first turned his improved telescope toward Jupiter in January 1610, he expected nothing more than a brighter view of a familiar wandering star. Instead, he found 3 tiny points of light positioned in a line beside the planet, then 4. Over the next nights, he observed them shift their positions not freely, but in orbit. Sometimes one disappeared behind Jupiter, only to re-emerge later, completing its silent circuit. Galileo kept detailed notes, sketching the nightly changes with the caution of a man aware he might be witnessing something unprecedented. Soon the pattern became undeniable. These were moons, satellites that did not orbit Earth. In that moment, Jupiter became a miniature solar system, and the Earth lost its monopoly over motion in the universe. This discovery carried profound implications. Aristotelian cosmology insisted that everything in the heavens revolved around Earth, perfect and immutable. Galileo's 4 Jovian moons, later named Io, Europa, Ganymede, and Callisto, defied that system openly. Here was celestial motion that did not include Earth at all. The discovery shattered the symmetry of the geocentric model, proving that centers of motion existed elsewhere. What centuries of argument failed to overturn, a small telescope accomplished with light and patience. Jupiter's moons were not just new objects in the sky. They were evidence. Evidence that could be seen, drawn, proven, and shown to anyone willing to look. The second revelation arrived when Galileo turned his telescope towards Venus. To the naked eye, the planet appeared only as a bright star. but through his lenses it revealed a sequence of phases: crescent, half, gibbous, exactly like the moon. This could not occur if Venus orbited Earth. In the Ptolemaic system, Venus would never appear fully illuminated or clearly crescent-shaped. Yet Galileo saw it change night after night, shrinking and expanding like a lamp behind a curtain. The phases of Venus provided something stronger than philosophical argument: geometric certainty. Only if Venus circled the sun could such phases exist. The heavens themselves were speaking, and what they said supported Copernicus, not Aristotle. Together, the moons of Jupiter and the phases of Venus formed a double blow to Earth-centered cosmology. The telescope had forced open the sky, revealing a universe governed by motion, structure, and order, independent of human assumption. Galileo sketched each observation carefully, publishing his findings in Sidereus Nuncius, the Starry Messenger, and later works that circulated across Europe like sparks through dry grass. These discoveries did not merely add knowledge, they changed the framework of knowledge itself. With each orbit traced and each phase recorded, Galileo pushed humanity closer to the realization that Earth was not the center of all things, but one moving world among many. The heavens were no longer unreachable perfection. They were landscapes to be explored, measured, and understood. And through Galileo's glass, mankind began to see the universe as it truly is. Galileo's astronomical discoveries did not merely intrigue him, they pushed him toward a bold and dangerous conclusion: that Nicholas Copernicus had been right. The Earth, he now believed, was not the fixed center of the universe, but one planet in motion around the sun. His telescope had shown moons circling Jupiter and phases unfolding across Venus, phenomena that fit perfectly into the heliocentric model. Galileo took these findings not as speculation, but as demonstration. Nature itself had presented evidence, and Galileo refused to ignore what the sky revealed. This conviction separated him from many scholars of his time, who still clung to Aristotle's unmoving Earth like an anchor of certainty. Galileo expressed his support for heliocentrism cautiously at first, aware that such ideas could provoke theological resistance. In private letters and academic discussions, he argued that Scripture described appearances rather than physical mechanics, and that God's creation was best understood by the laws he had written into nature. For Galileo, observation was not rebellion. It was worship through understanding. The universe, measured with instruments and reason, proclaimed divine order more clearly than inherited doctrine. Yet even these measured arguments unsettled conservative scholars who feared that Copernican astronomy threatened philosophical and religious tradition. The Earth had been the stage of creation for centuries. To move it from the center was to shift humanity's place in existence. By the 1610s, Galileo stepped more openly into the Copernican camp. His book, Letters on Sunspots, compared solar rotation to planetary motion, while his correspondence with theologians sought to reconcile scientific findings with biblical interpretation. Galileo did not see conflict where others did. To him, science revealed the mechanics of God's work. Theology revealed its purpose. Reason and faith, properly understood, were rivers flowing towards the same sea. The reluctance of academic authorities and the Church only intensified his determination. If the heavens showed the Earth in motion, Galileo argued, then truth, no matter how unsettling, must be acknowledged. His most direct defense of heliocentrism appeared in 1632, when he wrote Dialogue concerning the two chief world systems. Presented as a debate between three characters, The work dismantled the geocentric model through logic, observation, and gentle but unmistakable satire. Galileo attempted diplomacy by framing the book as discussion rather than doctrine, yet the message was clear. Evidence favored the sun-centered universe. With this publication, Galileo crossed a threshold from astronomer to revolutionary. Supporting Copernicus was no longer private conviction, it was public challenge. The Earth moved, the sun did not, and the weight of centuries was beginning to shift. Through Galileo, heliocentrism was no longer a theory whispered among scholars. It became a vision of the cosmos that changed how humanity understood itself. Galileo's embrace of heliocentrism placed him at the center of a collision between scientific evidence and ecclesiastical authority. Two forces that, in 17th century Europe, were tightly bound yet deeply uneasy with one another. At first, the Church tolerated discussion of Copernicus's theory, so long as it remained framed as mathematical hypothesis rather than physical truth. But Galileo's observations went further. He claimed that the telescope had revealed a universe inconsistent with Aristotle and Ptolemy, foundations upon which much of church-endorsed cosmology rested. As he spoke more confidently of Earth in motion, whispers of concern circulated through the Vatican's intellectual halls. Scholars sympathetic to tradition viewed Galileo's conclusions as not merely incorrect, but potentially destabilizing. Ideas capable of unmooring theology from the heavens it described. The tension deepened when theologians interpreted heliocentrism as contradicting passages of Scripture that spoke of the Earth fixed in place. To the Church, cosmology was not only a matter of science, but of divine order. If Galileo was right, centuries of unified cosmic image would require reinterpretation. Galileo attempted to diffuse this conflict through careful argument, insisting that the Bible taught spiritual truth, while nature expressed physical truth, both originating from God, neither in contradiction. But his reasoning, no matter how measured, threatened established authority. To admit that Scripture required non-literal reading at the insistence of telescopic observation was, for some church officials, to surrender interpretive power to the sciences. In 1616, the conflict reached open confrontation. A committee of theologians declared heliocentrism formally heretical, and Copernicus's writings were suspended pending correction. Galileo received a private warning. He was not to promote or defend the idea that Earth moved around the sun. He remained free, but his voice was bound by caution. Even so, Galileo did not abandon his conviction. He continued to write letters, devise arguments, and gather allies among students, princes, and scientific patrons across Europe. His silence was not submission. It was tension coiled, waiting. The greater the restriction placed upon him, the more urgently he sought to prove that nature, when observed carefully, spoke with greater clarity than tradition. By the late 1620s, Galileo believed circumstances had shifted. Friendly voices in the Vatican suggested dialogue was again possible, and he began drafting the work that would ignite formal crisis. Dialogue concerning the two chief world systems. Presented as balanced debate, it was in fact a methodical dismantling of geocentric thought. Published in 1632, the book circulated rapidly, stirring fascination and alarm. What had been simmering conflict became explosive confrontation. Galileo had challenged authority not by defiance alone, but by argument and demonstration. The Church, feeling its intellectual ground tremble, prepared to answer, not with telescopes, but with judgment. The stage was now set for trial, and the quiet tension of years hardened into irreversible collision. In 1632, Galileo released the work that would cement his place in history and simultaneously bring him into direct collision with the most powerful institution of his age: dialogue concerning the two chief world systems. The book was structured as a conversation between three interlocutors: Salviati, representing the Copernican view; Sagredo, an open-minded observer; and Simplicio, defending traditional Aristotelian cosmology. This format gave Galileo freedom to compare ideas directly, testing each claim through logic, observation, and natural reasoning. From the very first pages, the work radiated wit, precision, and intellectual pressure. Through courteous debate, Galileo dismantled geocentric assumptions piece by piece, lending the Copernican heliocentric model the sharpest defense it had ever received. The dialogue was not simply a scientific publication, it was a seismic event. Readers across Italy and Europe were captivated, turning pages as if reading a drama rather than astronomy. Galileo's language was accessible, not cloaked in academic obscurity, and thus reached merchants, scholars, nobles, and curious citizens alike. The book was evidence made visible to the lay reader, empowering those outside the scholarly elite to question inherited truth. It was this accessibility that unsettled church authorities most deeply. The heliocentric model was no longer confined to academies. It was entering households, disturbing certainty, and tilting the intellectual balance of Europe toward a new view of the cosmos. Despite Galileo's effort to present the book as balanced dialogue, the tone and content leaned unmistakably toward Copernicanism. Salviati's arguments were sharp and confident, while Simplicio often appeared rigid, even foolish, a portrayal many suspected was a veiled critique of conservative theologians. Whether intended or not, the impression was clear. Reason favored a sun-centered universe. Within months, whispers reached Rome that Galileo had broken the 1616 injunction forbidding him from advocating heliocentrism as truth. What Galileo viewed as philosophical exploration, the Church interpreted as public challenge. The pages that Galileo believed showed harmony between science and faith were read by others as an assault on accepted doctrine. In the summer of 1632, the dialogue was banned, and orders were issued for Galileo to appear before the Holy Office. The publication that had promised to illuminate the world instead cast a long shadow over its author. With this book, Galileo had crossed the threshold from scholar to revolutionary, one who dared show that the heavens contradicted tradition. The dialogue did not merely present two world systems, it placed them side by side and asked the reader to choose. It was a mirror held up to the universe, and in it, humanity saw, perhaps for the first time, that Earth might not be the center of creation. The ink of Galileo's words had set history in motion, and there would be no turning back. When Galileo was summoned to Rome in 1633, he was 70 years old. His body weakened, his eyesight fading, yet his mind still ablaze with discovery. He traveled under compulsion, escorted rather than welcomed, entering a city where power echoed through marble corridors, and silence weighed more heavily than debate. The Roman Inquisition was not a place of open argument, but of judgment, authority, and theological certainty. Galileo arrived knowing the stakes. He was to answer for the dialogue, a book the Church believed had crossed from inquiry into disobedience. Inside the Vatican's chambers, the scientist who had measured the heavens with lenses and mathematics now found himself measured by doctrine. The trial unfolded through a series of interrogations, each designed not to explore the truth of the cosmos, but to determine Galileo's obedience to the Church's command. He was questioned about his support for heliocentrism, about the meaning of his dialogue, and about whether he had violated the 1616 decree that forbade him from teaching Earth's motion as reality. Galileo defended himself carefully. He insisted he had only presented Copernican theory as hypothesis, and that the dialogue was intended as philosophical discussion, an exchange of ideas rather than a declaration of fact. But the inquisitors, reading every sentence through suspicion, found intention beneath neutrality. To them, his scientific reasoning overshadowed the cautious framing. The balance he believed he had built was judged a mask. In the final stages of the trial, Galileo stood in the presence of cardinals and theologians, facing not a scientific argument, but a moral demand: recant or condemn yourself by resistance. Evidence gathered from the heavens was weighed against Scripture, interpreted literally, and authority held greater mass than any telescope. Galileo, aware of the danger and the fate that could befall a man who defied holy judgment, bent beneath the pressure. On June 22, 1633, he formally abjured his support for heliocentrism. A lifetime of observation was compressed into a statement he did not believe, spoken to satisfy the court, not the universe. Tradition triumphed over proof. Though the recantation spared his life, it marked a moment of profound rupture in the history of knowledge. The Inquisition pronounced Galileo vehemently suspect of heresy and sentenced him to lifelong restriction. Forbidden to teach, publish, or advocate for the motion of the earth, he left the trial as a man silenced but not defeated internally. Behind the official record, a legend would later whisper that as he rose from sentencing, Galileo murmured, "Et pour si muove." And yet it moves. Whether or not the words were spoken aloud, they embodied the truth of that moment. The earth did move, the sun did not circle it, and no decree could alter the sky. The trial of Galileo was not only the judgment of a man, it was the beginning of the world learning that truth cannot be imprisoned, even when its voice is forced to bow. After the verdict of 1633, Galileo was confined first to the palace of the archbishop at Siena, and later to his own villa at Arcetri, near Florence, an exile not from land, but from intellectual freedom. The rooms that once housed conversation, experiment, and students now echoed with restriction. His movements were monitored, his correspondence screened, and visitors allowed only under supervision. Yet confinement did not silence the mind that had opened the heavens. If anything, isolation distilled his thought into sharper clarity. Galileo's house became his observatory, his library, his universe. Here, surrounded by Tuscan hills and the slow turning of seasons, he continued to reason about motion, mechanics, and the laws that govern bodies in motion. Despite failing eyesight, and eventually near blindness, Galileo dictated new work that pushed beyond the astronomy that had shaken the world. Denied the telescope as his voice, he turned to motion itself. Falling bodies, inertia, resistance, and the nature of acceleration. His scientific exile became a laboratory of intellect. Servants and students served as his eyes, reading aloud, recording his calculations, and hearing the shape of theory form in his speech. The aging philosopher, confined by decree, continued to test nature through thought experiment rather than instrument. His mind remained free where his body was locked, proving that knowledge is a realm no authority can fully bar. From this enforced quiet came one of his greatest works, discourses and mathematical demonstrations relating to two new sciences, completed in the late 1630s. In it, Galileo laid the foundation for classical mechanics. He described the mathematics of accelerated motion, the behavior of projectiles, and the principles of material strength. What began in youth with swinging lamps and rolling spheres matured here into formal theory. The book was smuggled to the Netherlands and published beyond the Church's reach, ironically ensuring that the work produced in confinement traveled further than any he had written in freedom. The world that sentenced him to silence now heard him more clearly than ever. Galileo lived under house arrest for nearly a decade, guarded by decree but driven by insight until his death in 1642. His home became both prison and workshop, a place where punishment produced progress. While his telescope no longer guided his hand, imagination and mathematics guided his legacy. In those final years, Galileo proved that ideas endure even under chains. The truth, once seen, cannot be unseen. His confinement did not end his science, it completed it. The scholar who once looked upward with glass finished his work looking inward with reason, leaving behind not a broken philosopher, but a founder of modern physics whose greatest discoveries were born in darkness, yet destined for light. Galileo's work on motion grew from a lifetime of careful observation and experimentation, a discipline rooted not in speculation, but in the physical behavior of objects. Long before his conflict with the Church, he had realized that nature did not follow the rules Aristotelian philosophy insisted upon. According to tradition, heavier objects fell faster than lighter ones, moved by an intrinsic tendency toward their natural place. Galileo doubted this view and began to test motion directly, rolling spheres down inclined planes to slow the fall enough that he could measure it. What centuries had treated as unquestionable law became a question answered by experiment. With wooden ramps, marked distances, and water clocks, Galileo traced acceleration not by assumption, but by number. His experiments revealed something extraordinary, that falling bodies accelerate at a constant rate regardless of mass. A cannonball and a pebble, dropped from the same height, would strike the ground nearly together, not because of weight, but because gravity acted uniformly upon them. Galileo recorded timings, plotted distances, and noticed a square relationship. In equal intervals of time, falling bodies gained equal increments of speed. This insight, simple yet revolutionary, introduced mathematical precision into the study of motion. No longer was falling a mysterious tendency. It was measurable, predictable, and governed by law. Through Galileo, motion ceased to be philosophy and became physics. Beyond free fall, Galileo developed a new understanding of inertia. He proposed that an object in motion continues without change unless acted upon by an external force, a principle radically opposed to Aristotelian belief that motion must be constantly driven. Galileo imagined a body sliding across a perfectly smooth surface. Without resistance, it would move indefinitely. Though the world offered no frictionless plane, the idea revealed a deep truth: motion sustains itself. This insight formed one of the cornerstones of mechanics, later refined by Newton into the first law of motion. What Galileo produced through thought and experiment became the foundation of classical dynamics. Projectile motion also fell within his scope. Cannons and catapults were common in his world, yet their arcs defied simple geometry. Galileo realized that a projectile's path combined horizontal inertia and vertical acceleration, producing a parabola, a curve defined by mathematics, not chance. Through diagrams and proofs, he demonstrated how distance, speed, and angle determined trajectory. Soldiers, engineers, and astronomers now shared a common framework. Motion obeyed geometry. With each conclusion, Galileo tightened the thread between mathematics and nature, showing that the universe could be read like a book, if one knew the language of measurement. In his final years, Galileo consolidated decades of study into two new sciences, a work written under house arrest, but intellectually unbound. Here, the laws of falling bodies, inertia, and material strength emerged with clarity and permanence. These were not isolated ideas. They were the blueprint of modern mechanics, the groundwork upon which Newton would later build universal gravitation. Galileo's studies of motion transformed science forever. He lifted movement out of philosophical speculation and placed it into the realm of proof, experiment, and mathematical law. In doing so, he reshaped the way humanity understands the world, not through authority, but through reason measured in motion itself. Galileo Galilei died on January 8, 1642, within the quiet walls of his villa in Arcetri, an old man nearly blind, confined by decree, yet undefeated in spirit. He left the world much as he had lived within it, watching, reasoning, and questioning until the final days. The official church still forbade him from teaching heliocentrism, and his movement was limited by the terms of his sentence, yet his mind remained active. Conversations with pupils continued in hushed rooms, manuscripts whispered into the hands of confidants, and ideas that could not be spoken aloud traveled through ink instead. Even as his body weakened, he remained a thinker poised between two eras, one still bound to tradition, the other beginning to awaken to scientific truth. Galileo did not live to see vindication, but his final breath carried the certainty that the earth moved, no matter who denied it. In the decades after his death, his influence rippled outward like waves from a dropped stone. Students and followers preserved his writings, smuggling them beyond censorship into the intellectual currents of Northern Europe. There, his insights met minds ready to build upon them. Isaac Newton would later write, "If I have seen further, it is by standing on the shoulders of giants." And Galileo was among the giants he meant. The laws of motion Galileo discovered became Newton's foundations. The telescope Galileo refined gave birth to astrophysics. The insistence on experiment over assumption became the heart of scientific method. Through the work of later physicists, engineers, and astronomers, Galileo lived on, not as martyr, but as architect of modern inquiry. As centuries passed, the church that once condemned his teaching eventually acknowledged its truth. The earth does move, planets circle the sun, the moon is cratered and real, Jupiter carries its own system of worlds. Every telescope pointed toward the sky confirms what Galileo first glimpsed through ground glass and persistence. His name now stands beside the very laws he helped define. Pendulum clocks trace time to his rhythm, satellites obey the inertia he described, and spacecraft follow parabolic paths just as he predicted with geometry and ink. The universe itself proved him right more fully than any council could deny. Galileo's legacy endures not only in discoveries, but in attitude. He taught the world that authority cannot replace evidence, that nature is the ultimate scripture of science, and that curiosity, armed with patience and instrument, can overturn centuries of certainty. His life marked the turning of a page in human understanding, a moment when the night sky ceased to be myth and became measurable. The child who once timed swinging lamps by pulse became the father of modern physics, and the prisoner of Archetri became the liberator of human thought. In the long arc of history, Galileo did not fall. He accelerated, and the world, still moving, continues to follow the path he traced into the stars.